Welcome to This Explainer. I'm your host, and today we're going to unravel the physical reality of two of the absolute most fundamental concepts in the universe: power and energy. And listen, we're not just going to sit here memorizing textbook formulas, all right? We are going to build a deep, intuitive understanding of this stuff right from the ground up. Okay, let's dive into this. Have you ever stared at your smartphone screen as it hits that dreaded 1% and wondered, why does a battery actually run out? I mean, why don't they just last forever? Before we look at a single equation or scientific definition today, I really want you to think about this everyday mystery. When your battery dies, what exactly ran out? Did you run out of electricity? Or did you run out of something else entirely? To answer that, we really need to understand what energy actually is from a physical perspective. Energy is the actual capacity to do real physical work. It's the fundamental ability to move things around, to create heat, to generate light, or, to spin a motor. Now, here is a massive misconception that trips up beginners all the time. Electricity itself is not energy. No way. Electricity is just a vehicle. It's an invisible messenger that simply transfers energy from one place to another. And this brilliantly illustrates that idea. Whether we're talking about direct current, where those electrons are just marching steadily in one direction, or alternating current, where they're kind of oscillating back and forth like a pendulum, notice that the electrons themselves aren't actually consumed by your device. They're literally just acting like little delivery trucks. They carry the energy from a source, drop it off at a load, and just head back to get more. So if electricity is just the delivery truck, where is the cargo coming from, right? Well, the magnificent law of conservation of energy tells us that energy is never magically created out of thin air. It's only ever transformed. Take our power grids, for example. That electrical energy actually starts its life as mechanical work. We take the intense boiling heat of superheated steam or the immense pressure of rushing water, and we use it to physically spin a massive turbine. That mechanical turning motion drives a generator, which transforms that mechanical energy into an electrical form. And then the electricity just carries that harnessed energy right out to the grid. All right, let's put a formal scientific name to this energy. Enter the joule. It's named after the 19th century physicist James Prescott Joule, and it's the standard SI unit of energy. But what is a joule in the real physical world? Well, physically, 1 joule represents the exact amount of mechanical work it takes to push a weight of 1 newton over a distance of 1 meter. So to put that into perspective, if you pick up a small object, like say an apple, and lift it up to about your waist against gravity, congratulations, you've just done about 1 joule of real physical work. It's a highly tangible measurement of effort. Let's translate this physical reality into some mathematical shorthand. Remembered our number 1 rule here? Energy equals work. They are the exact same physical thing. Now, to find the total electrical energy, we take voltage, which is the electrical pressure, we multiply it by current, which is the flow of our messengers, and then we multiply all of that by time. That tells us exactly how much work those messengers did while they were out there flowing. And looking at it from another angle, energy also equals power multiplied by time. We're going to define power in just a second, but I want you to notice that time is an absolutely critical, unavoidable factor for measuring the total energy you've consumed. Now, you might be wondering, if we already have this perfect way to measure the total amount of energy, our joules, why did engineers and physicists ever need to invent the concept of power? I mean, why isn't knowing the total energy alone enough to design a circuit or build a machine? Think about what actually happens when you flip a switch and turn a device on. What's the missing piece of the puzzle here? Well, the missing factor is speed. You see, knowing you have 1,000,000 joules of energy sitting around is great, but it tells you absolutely nothing about how fast you're using or transferring that pool of energy. Power is simply the rate at which work is done. Are you dumping all that energy in one single second, causing a massive explosion of heat? Or are you sipping that exact same amount of energy slowly over a whole year? That rate of transfer, that speed, is what we call power. So the crucial point is how we measure this speed scientifically. We use a unit called the watt. By definition, 1 watt is exactly 1 joule of energy transferred per single second. So if you're holding a tiny 1 watt electronic device in your hand, it is physically absorbing and converting 1 joule of energy every single second that it's turned on. Wattage, remember, isn't an amount, it's a rate of flow. Okay, let's look at the essential power equations. Really, just think of these as a logical shorthand for the physical reality you just grasped. Power equals energy divided by time. That's our basic definition of joules per second. Now, in a direct current circuit, power simply equals voltage times current. And since Ohm's law tells us that voltage equals current times resistance, we can just sub those variables in. So power also equals current squared times resistance, or voltage squared divided by resistance. An engineer is basically going to choose exactly which of these formulas to use depending on what they're actually testing, whether it's the voltage supply, the current flow, or the physical resistance of the device. Let's solve a simple conceptual example together to really cement this. Imagine you park your car, but you accidentally leave the parking lights on. Happens to the best of us, right? Your car has a 12-volt direct current battery, and those incandescent lights are drawing a steady combined current of 4 amps. Using our handy power formula, voltage times current, 12 volts times 4 amps gives us 48 watts of power. That means those lights are consuming 48 joules of energy every single second. Now, if you leave them on for exactly 1 hour, which is 3,600 seconds, you just multiply 48 watts by 3,600 seconds. That results in a massive 172,800 joules of total energy drained straight from your battery in that hour. No wonder the car won't start. Now, if you ever find yourself getting confused between these two concepts, which is totally normal, by the way, I want you to just picture water. Energy is basically equivalent to the total volume of water sitting in a giant storage tank. Power, on the other hand, is the rate at which water is actively spraying out of the hose connected to it. A huge tank can empty super slowly through a tiny hose, so that's high energy but low power. Or it could empty in 5 seconds flat through a massive industrial pipe. That would be high energy and high power. The total amount of water doesn't change, just the speed of its delivery. All right, I'm going to let you in on a little secret that trips up so many students when they first study alternating current. Not all power actually does physical work. There is a component called active power, sometimes called real power, and that's the energy that actually creates heat, lights up your living room, or spins a motor shaft. But because of sneaky components like inductors and capacitors in AC circuits, we also have reactive power. Reactive power is completely, literally, wattless. It's this oscillating energy that just bounces back and forth between the power source and the load, kind of like a tennis ball, doing absolutely zero net physical work. Understanding this delicate balance is the true heart of power engineering. So why must engineers, especially biomedical engineers, absolutely master these concepts? Think about life-saving medical devices. A defibrillator needs to deliver a massive, instantaneous spike of power. We're talking hundreds of watts in a tiny fraction of a second just to restart a heart. An X-ray machine needs a meticulously managed burst of high energy to actually penetrate tissue. Meanwhile, a continuous patient monitor relies on sipping tiny amounts of low power over days and days to ensure that battery never dies. Out in the real world, safety and survival rely entirely on mastering joules and watts. Let's move to our final thought and see how this all builds together. We now know that electricity is just the messenger. We know power is the speed of delivery, and energy is the fundamental capacity to do work. But what forces the messenger to actually move in the first place? What actually pushes those electric charges through a circuit? Well, that invisible push is called voltage, or electric potential difference. Thank you for joining me, and keep questioning how the physical world works.